the fourth day of probability, which is events occurring together. So I want to begin by talking about given probabilities. So what is a given probability? A given probability is the following. If we let A and B be events, whatever they might be, doesn't matter, then the expression let me write it this way. This expression right here has the following meaning. It means the probability that B occurs given that A has already occurred. So this expression here, you'll notice that, yeah, there's these two events inside the parentheses, and there's this big vertical bar in between them. This is the probability that B occurs given that A has already occurred. If you like, the vertical bar sort of means given. For short, this is often just pronounced probability of B given A. And I want to explain just briefly what this really means. The idea is that you've got these two events, A and B, and the idea is that the occurrence of event A may have some influence on the occurrence or non-occurrence of event B. In other words, the probability of B occurring could be influenced by whether or not the other event, A, has already occurred. So asking what's the probability of B given A is saying what's the probability of B occurring assuming, given the fact that this other event, A, has already occurred. That's the idea. And we'll take a look at an example. So here's the example. Suppose you have a bag. We're going to use this example a lot in the coming days. You have a bag with a bunch of marbles, which, if you remember, marbles are like these little balls. So suppose you have a bag and you have 15 red marbles and you have 10 green marbles, okay? And the situation is you reach into the bag, you pull out one, and then you pull out another without replacement, okay? Without replacement. So what that means is, you know, you reach in, you pull out one marble, you don't put the first marble back, you set it aside, you reach in, you pull out a second marble. And here's the question. What's the probability? What's the probability that the second marble is green given that the first was red? Okay, so you see the presence of this word given here. That means we're going to be looking at something like this. So I'm asking, you know, what's the probability that your second marble is green given, assuming the fact that your first marble was red? If we wanted to represent this using this notation, then perhaps we could write it this way. It's the probability of, well, we want to know the probability that the second marble is green. To represent second marble as green, I'm just going to write 2G. And we want to know what's the probability that the second marble is green given, vertical bar, the fact that the first marble was red. And first marble being red, I'll represent by writing 1R. So this is the probability that the second marble was green given the fact that the first marble was red. So, you know, I mean, look, originally there were 25 marbles in the bag, but assuming, given the fact that the first marble was red, you know, we've already taken out one red marble. That means there are now only 24 marbles left in the bag. Okay, and of those marbles, how many of them are green? Well, since we're assuming the first marble was red, that means that there are still 10 green marbles left in the bag. So the answer is 10 out of 24. Okay, so that's an example of given probability. The next thing I want to talk about is consecutive events, which will use this given probability stuff. So consecutive events. So here's the idea. The probability that A occurs and then B occurs is given by, and there's a formula for this, okay? And once I write down the formula and explain it, you'll see why it's got to be true. So the idea is, you've got these two events, A and B, and I want to know what's the probability that A occurs and then after that event B occurs. Symbolically, what we write is the probability of A intersect B. So a quick note on this notation, you might remember this upside down U means the intersection of A and B. It really just means and. So this is the probability that both A and B occur. In the way that I've set this up, I've sort of made it seem like we're specifically talking about event A occurring and then event B occurring later in time. It is often helpful to imagine that the events are occurring in sequence, like first A happens and then later in time B happens. But the formula that I'm about to give you actually works even if events A and B are simultaneous. It works even if event B comes before event A. But understanding why this formula works is a lot easier if you imagine that event A is occurring and then later in time event B is occurring. Although you can use this formula even when that's not the case. So here's the formula. The probability of A and B, or if you like, probability of A and then B, is given by the probability of A times the probability of B given A. Okay, so that's the formula. Let's just try and understand why this makes sense. This is the probability, so the probability that A happens and then B happens is the probability that A happens times the probability that B happens given the fact that A has already occurred. Okay. Let's take a look at this example. And the notation is very abstract, but as you'll see, it's actually pretty straightforward. So I'm going to keep using that same example, right? We've once again got this bag, and we've got, I think I said, what did I say, 15 red and 10 green, is that right? Yeah, 15 red and 10 green marbles. We're going to keep using that example. So 15 red, 10 green. And I'm going to say find the probability of getting red then green. Okay? Or if you like, red and then green. So what I'm really saying is find the probability that the first marble is red. Right? So find the probability that the first marble is red and that the second marble is green. So represented using symbols, this is the thing that I'm looking for. It's the probability that the first marble is red and the second marble is green. Or if you like, if you want to emphasize like the sequence of things in time, you can say it's the probability of the first marble being red and then the second marble being green. Okay, so according to our formula, that's going to be just the probability of the first marble being red times the probability of the second marble being green given the fact that the first marble was red. Okay? So let's compute these things. So probability that the first marble is red, well, there are 15 red marbles out of 25 marbles in the bag, so that's 15 out of 25. The second one, the probability that the second marble is green given that the first marble was red, well, understanding that the first marble was red, we know there are now only 24 marbles in the bag. And of the remaining marbles in the bag, all of them are green because the first one was red. So there's still 10, sorry, not all of them are green, but I'm saying all of the green marbles are still left over, right? There are still 10 green marbles left in the bag. And that's it. That's all it is. Okay? And as you'll see, if I do another example, so same exact example, but this time, let's say, what's the probability of getting green followed by green? Okay, well, that's going to be the probability that the first marble is green, which is 10 out of 25, times the probability that the second marble is green, given the fact that the first marble was green. Well, given the fact that the first marble was green, there are only 9 green marbles left in the bag out of 24. So that's what that would be. And you can see right away that, yeah, despite the fact that we used this fancy formula, it's actually like very logical. What's the probability of getting red, red, green, right? So I guess we're pulling out 5 marbles now, one at a time. Well, it's the probability of getting red, so that would be 15 out of 25 times, and then red again. Okay, now there are 14 red marbles out of 24 times, okay, back to, now we're doing green. Well, there are still 10 green marbles left in the bag, but only out of 23, right? And then back to red, okay, there are 13 red out of 22 total, and then finally back to green, there are now 9 green out of 21. So whatever this thing is, that's the probability. Okay, it really is that straightforward. Okay, so the last thing I want to talk about today is a so-called tree diagram. Now, a tree diagram is a way of representing every possible thing that can happen in some probability situation. It's a way of diagramming all the possibilities, and at the same time kind of keeping track of all of the different probabilities involved. And they're a nice way of organizing things, but they're also really important for harder probability questions that we'll be looking at in a couple of days. So let's take a look. What I'm going to do is I'm going to make a tree diagram for the situation that we've been, looking at again and again. We've got a bag with 15 red and 10 green, and I'm just going to say we're pulling out 2 marbles. Okay, we're pulling out 1 marble and then another one. So that's the situation for which I want to make a tree diagram. So the first thing you do is you reach into the bag and you pull out your marble, and what are the 2 things that can happen? Well, could be green or could be red. That gives me 2 branches of my tree diagram. I draw my tree diagram sideways. You can draw them vertically if you want. I just find it more convenient in terms of like saving paper space to draw them horizontally. Okay, so there are 2 possibilities, red or green, and I'm going to label the branches. I'm going to write R above the first branch and green above the second branch to represent that this branch represents getting red, this one represents getting green. And then below the branches, I'm going to write the probabilities of those events occurring. So what's the probability of getting red on the first withdrawal? Well, that's going to be 15 out of 25. And how about the probability of getting green on the first one? That would be 10 out of 25. Is that okay? And then of course, we're withdrawing a second marble, so these branches split again, right? So this one splits here, again corresponding to the possibility of getting red or green. This is for the second marble now. And this one also splits again, right? You could get red or green on here. Now, I'm going to write a number here. The number I'm going to write here is the probability of getting red given the fact that I am already on this branch. In other words, it's the probability of getting red given the fact that my first marble was red. That's going to be 14 out of 24. Here, I'm going to write the probability of getting green given the fact that my first marble was red, given the fact that I'm already on this branch here. Well, that would be 10 out of 24. Now I go down here. This is going to be the probability of getting red given the fact that my first marble was green, given the fact that I'm on this branch here. That's going to be still 15 out of 24. And then this is going to be the probability of getting green, given the fact that my first marble was green. That's going to be 9 out of 24. So I hope it's clear. These things are given probabilities, right? All right. And then there's one more thing I'm going to add to my tree diagram. At the end of each branch, I'm going to write a new number. So right here, I'm going to write the product of all the numbers along the path ending in this branch. So that would be 15 out of 25 times 14 out of 24. So 15 out of 25 times 14 out of 24. And then same thing here. I'm going to write another probability, another number here, which is the product of all the numbers along this path, right? The path ending at this point. That would be 15 out of 25 times 10 out of 24. And then same thing here. That would be 10 out of 25 times 15 out of 24. And then finally 10 out of 25 times 9 out of 24. I call these things end branch probabilities. End branch probabilities. They're at the end of the branch. But what do they represent? This thing here is the probability that it's the probability that these events occur in sequence. It's the probability that your first marble's red and your second marble's red. That's the probability that your first marble's red and your second marble's red. Be the probability that your first marble's red and your second marble is green. Okay, so that's what these things represent. Okay. Okay, so I could just ask you some random questions. Like I could be like, hey, here's a diagram. What's the probability that the second marble is green, given the fact that the first marble is green? Think about where that would be on the diagram. So assuming that the first marble was green, in other words, assuming that you're on this branch here, what's the probability that your second marble is green? That'd be this guy right here, 9 out of 24. Okay, on the other hand, I could ask, what's the probability that the first marble is green and the second marble is green? That's the probability that the first marble is green, and then after that, the second marble is also green. That's a different thing. That's going to be this guy right here. That's 10 out of 25 times 9 out of 24. The difference between these two things is, in this one, we're assuming that the first marble is green. We're sort of like taking it for granted. Here, we're not assuming that the first marble is green. So the probability that the first marble is green actually comes into play. Okay. And I can ask you lots of other questions about this, but the point of tree diagrams is they allow you to answer harder questions. Okay, here's sort of a trickier one. What's the probability, well actually one more easy one, what's the probability that the first marble is green? Just straight up. Well, you can see that from the diagram. 10 out of 25. No problem. Here's a much more interesting question. What's the probability that the second marble is green? It's interesting. What's the probability that the second marble is green? If you look at the diagram, there's not really anything that corresponds to that exactly. The truth is that second marble being green corresponds to multiple branches in the diagram. Second marble being green corresponds to both this branch here and also that branch. It's like this event is spread out over multiple branches. When that occurs, you have to add all of the end branch probabilities together. So second marble being green, which branches correspond to that? This one, so I'm going to write down 15 out of 25 times 10 out of 24 plus, and then this branch also corresponds. So 10 out of 25 times 9 out of 24. The logic behind the plus is that we're basically breaking it into cases. Like the event second marble being green can occur in two ways. You could have first marble red and second marble green, or you could have first marble green and second marble green, right? Those are the two ways that it could happen. So you're breaking up the event, second marble green, into those two cases. And you find the probability of each of those two cases, and then you add them together. That's what we're doing here. Okay? So the lesson here is anytime you have a question which involves multiple branches in the diagram, you need to add up all of the associated end branch probabilities. So if I say, here's another one, what's the probability that the two marbles are the same color? Okay, now if you think about that, the probability that the two marbles are the same color, there are actually two, and there are two branches corresponding to that, right? It's this branch here, red, red, but also this branch here, green, green. Because that event corresponds to multiple branches in the diagram, we got to add all of the end branch probabilities together corresponding with that event. That's these two guys right here. So the answer would be this thing plus this thing. I'll just leave it at that. Okay.